All right. So welcome to the final exam, get together, study session, whatever you want to call it. Before we get to it, let me just go over a few things that I've been working on the weekend and this morning for Blackboard. So I'll share my Blackboard screen. So first off, don't forget about the final exam take-home portion. That's due on Monday. Just saw my announcement, hopefully, and sorry to spring this on you last minute like this, but we have to do like assessments, and one of the assessments we have to do is writing, which is kind of hard for general chemistry. And originally I planned to put this in the final exam, like I said, but after coming up with topics, I figured it would be less stressful for you not to have this just show up on your final exam. So that's why I've decided to like have it be another take home part 2 almost, except it's due on Wednesday. And it's just how taking chemistry has changed how you look at like the world or any recent events and how you can relate that to what you've learned. Nothing too fancy, just like 3/4 of a page, double space. And that'll be good for that. Like I said in the announcement, it'll pad your grade for the final exam. So it's kind of like a reading guide in that respect. So there's that. I put up an equation sheet for you to use on the final exam in case, so it has all your equations in one spot. Feel free to download it, write on it whatever you want, because the final exam is going to be open note, just like the regular tests. I put up a new geometry sheet for those of you who said that the old one was too blurry to read. So this is another one I found. It's the same type of idea, it's just a different layout. So on this column that I'm going over, that's how many groups you have connected, bonding and lone pairs. Here is the electron geometry for those number of groups. Here are molecular geometries with lone pairs. So for example, in the bent conformation here, you have 4 total groups. 2 of those are lone pairs, and 2 of them are bonded. So same graph as we were looking at the word on the table version, just presented in a different way with pictures and different headers. So there's that. Last thing that I made for you are I just copied test 1, 2, 3, and 4. And you can take these and you can take them as many times as you want. That's why I have them as repeatable. They should be set up so you can do multiple attempts. And every time you do an attempt, I think you should be able to go and see if you got what was the answer you put in and then what the correct answer should be. I think these are very valuable because a lot of these questions that I created for the test, they will pick random variables. So when you do these, you'll get new variables and a new way to do the problem. And also why I think this will be valuable is that when we do the final, it's going to be made up of topics you have already been tested on. What I mean by that is if I didn't ask you like a question on test 1, 2, 3, or 4, or a topic on test 1, 2, 3, and 4, then I won't ask you that topic on the final exam. That does not mean the final exam will just be test 1, 2, 3, and 4 repeated. But if I talked about some topic or used an equation on test 1, 2, 3, or 4, there's a chance that it will show up on the final exam. So a good way to focus your studying is to look at those previous tests. All right, so those are just some random announcements that I wanted to go through. So let me open it up to you all who have attended. What questions do you have for me? Do you want me to go over any specific problems, any specific ideas, anything at all? Feel free to ask me anything you want, and I'll answer it to the best of my abilities. If you don't want to type stuff out, feel free to like raise your hand. You can do that on Zoom, and I can definitely unmute you if you like. Just keep in mind, I am recording this, so your voice will be captured forever on YouTube, or you can just type it out. So what questions do people have for the final exam? What do you want to know? What do you want to review? What do you want to go over? Time limit, 2.5 hours. Number of questions, I do not know because I have not made it yet. Let me see last semester how many questions I had. Last semester I had 41 questions. No, that is the wrong class. No, it's not. 41 questions. So you should have plenty of time to do that during the final exam. And do keep in mind though, even though this is open note, don't expect Google to help you out. Hopefully you figure out in the last 2 tests that I'm gonna like Google everything to make sure it doesn't show up. So you can't just Google and ask for questions. If I find that you have been posting my questions online, like you copy and paste and post it online, I will track you down and I will give you a 0 for the final exam. So don't do that. I've been pretty good at tracking people down this semester. Will you be using ProctorU? No, since this is open note anyways. I probably will not be using ProctorU. There's a good chance I will not be. Let me say that. What else do people have? What do you want to know? Is there any problem that, you went over in the tests, taking tests 1, 2, 3, and 4, you remember? I just don't remember how to do this. How can I see what I missed on test 4? Test 4 should be open. Let me just double check. I thought I did that this morning. It's very well possible I did not. Available students. Oh, I might still be hiding the actual raw grade. Gotcha. Let me go and look at that. So it's open for that section. Test 4, test options. All answers, correct, submitted. Submit that. Let me just double check that it's all good to go. Test 4 raw. It's on that. Test 4. It's on that. Okay. I think I let you see the test, but I didn't see which one. I didn't let you see whether it was correct or not. So that should all be good to go now. Is a repeatable test count towards your grades? No, they are not. They are not scored at all. You can just do them over and over and over again if you want. Like, I think my thought is that like doing the old tests is the best way for you to realize, oh, I don't remember how to do this problem. And hopefully it can focus you better, while stuff that you can get right, maybe you can not focus on that so much. So hopefully it's a good way to better use your time. That was the idea, at least. Can we go over question 4 on test 3? You have to tell me what the question is, because everybody has a different question 4. Actually, you don't. I just lied. I can look at your test and see which one was 4 for you. So let me take a look here. So you can't see test 2. All right, let me go and try and fix test 2 before I get to that question. Test 2. So test 2. Sure we're okay here. Okay, test 2 should be open for that section. Okay, test 2 should be able to be seen. Okay, so can we go over question 4 on test 3? Let me go back to that. Question 4, test 3. Look at your test 4. Oh, test 3. I'm not very smart today. I was looking at question 3, test 4. I'm like, what are you talking about? Question 3, test 4. Question 3. Test 4. Question 4, test 3. Okay, so well, it's when 1.46 grams of compound X burned in a bomb, the temperature raises from 29.5 to 2445. Find delta E. All right, so this is bomb calorimetry. So let me do share screen. And let me get a whiteboard. Okay. So the question is, let me get my pen back out. You have 1.49 grams of something. And this of compound X. Compound X has 250 grams per mole. That's the molecular weight. And then you burn it in a bomb calorimeter. So you burn it. And the temperature increases from 29.25 to 45.68. Let me move this over. Okay, so T initial is 29.25 0.25 T final is 45.68. Okay. And the heat capacity of the bomb is 4.23 kilojoules per centigrade. So 4.23 kilojoules per centigrade. What's delta E reaction in kilojoules per mole? Basically, what I'm saying here is if I have 1 mole of substance, when I blow it up, how many kilojoules of energy did I release? Right? So the first thing that I need to find is question 1 I need to ask myself. I burned 1.49 grams of something. How much energy was that? Keeping in mind that our unit of energy is the joule. And so we're looking for something that will tell us when we burn a substance, how much joules released. Well, our 2 things that can tell us that are temperature and the heat capacity of our bomb. So the heat that is released when we blow something up is 4.23 kilojoules of energy for every degree centigrade that we changed. And our change in temperature was 45.68 minus 29.28. These have units of centigrade. Centigrade cancel out, and I'm left with a unit of kilojoules. So let me do this math really quick for us. So we have 4.23 times 45.68 minus 29.28. So the amount of heat that was, in this case, I'm calculating how much was absorbed by our bomb, was 69.37 kilojoules. Or if I'm going to do sig fig, 69.4 kilojoules. That was absorbed by the bomb. The amount released was negative 69.4 kilojoules. Something to keep in mind, when something explodes, it's hot, right? So it releases energy. So we've released 69.4 kilojoules of energy. However, that's only part of my answer. I want to know how much energy is released when we blow up 1 mole of compound X. And so far, I found out that you get 69.4 kilojoules of energy when you explode 1.49 grams. So the units you can do is kilojoules per gram. From there, I can go from grams to moles. There are 250 grams for every 1 mole. Multiply that together. So take 69.4 times 250. Take that divided by 1.49. And the answer is roughly negative 11,640 kilojoules per mole. Looking at the test, what the test said, I'm off by like 20 kilojoules per mole. That's because I rounded like up here. So that's a rounding error. That's why in the test, usually I give some leeway. Like I compare your answer to what the computer calculated. And if you're close, I give you full credit. But that is how you do a bomb calorimetry. So when you release something, it becomes negative. Well, remember, this is energy we're talking about. So if you're standing in front of a bomb and it goes off, do you think that the bomb lost heat Or do you think it absorbed heat from the surroundings? Well, a bomb usually lets off heat because you feel that, right? You feel it being super hot. So if it's releasing heat, that means the bomb itself lost that heat. So the heat is negative, or the energy is negative. So yes, when you are releasing energy, your energy change is negative. Can you do a brief over finding the number of valence electrons for molecules? Sure. So the number of valence electrons. And unfortunately, I outsmarted myself when I asked this on test 4, because the compound I picked technically has 2 correct answers. It has the answer that I told you in class of how to find it, but it also has the answer that Google tells it, that technically on a chemistry level is correct, but nobody here should actually know that that's correct. So, I mean, I gave you full credit if you just looked up into Google, because that was my mistake. I won't make that mistake again. But anyways, let's look up let's do the electron configuration for the element let's actually do strontium. So strontium, element 38. So I'm going to do the full electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. The way to find valence electrons is you just look to the highest energy level. So the highest energy level here is 5. So strontium has 2 valence electrons. And let's do another example. Let's do bromine. Bromine's element 35. And it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. All right. For bromine, the highest energy level is the 4th energy level. And you have 2 different fourth energy level shells. You have the S shell and the P shell. And they're added together. So in total, bromine has 7 valence electrons. You have 2 electrons from the 4s orbital, and you have 5 electrons from the 4p orbital. Okay. Sure. So let me see. I'm trying to do these in order. So valence electrons. Yep. So another question is, atom X is a metal with 3 valence electrons. Is that on test 4 or something? Atom X is let me go look at test 4. Okay, let me go and look at atom X. Let me go look at the test 4 questions. Oh, yeah. This was actually a question that we went over in class. I just changed the elements. Instead of being the actual elements, I just changed them to X and Y. But the question is, atom X has 3 valence electrons. Valence electrons. Atom Y has 6. Whoops. Atom Y has 6 valence electrons. What is the compound that X and Y will make? Okay, so the thing you have to remember for this is the octet rule. And I also said that X is a metal, non-metal. Y is a non-metal. So you have to remember the octet rule, in which elements want 8 valence electrons. You have to remember that metals donate electrons. Non-metals take electrons or absorb electrons. So let me write Lewis structures for X and Y. So X has 3 valence electrons, Y has 6. So 3, 6. Remember, the goal here is to get to 8. And if there's a metal and a non-metal, you're going to form an ionic bond, because that's what metals and non-metals do, which means the metal will give it completely. So the metal will give 1 electron here and 1 electron here, which means that our X atom has 1 valence electron, and our Y atom now has 8. But we're not done yet, because the octet rule is not satisfied for this X atom. You either want 8 or 0, basically, because if you have 0, that means you lost electrons, and then you have a full octet from your other shell. So when we run into this situation, the thing to do is you have to bring in another Y atom, and that comes with 6 valence electrons. So that will give it to that Y. That Y has 7. This X will have 0. So let me just rewrite it neater. So right now we're in a situation where one X atom has given its electrons away to 2 Ys. That one's at 0, so that's happy. That Y has 8, that's happy. This Y has 7, that's not happy. So we have to bring in another X, which comes with 3. Give it here. X gives an electron to Y. Now it has 8. Bring in another Y, because right now we're at 2 valence electrons. That X isn't happy. So to get rid of valence electrons, we have to bring in another Y, give it here. Give the 2 electrons away here. This Y has 8. This X has 0. Let me rewrite it neater. And sorry, my Y's and X's look alike, I know. So this formula is to make a neutral compound. For every 2 X's, you need 3 Y's. Because when you have 2 X's for every 3 Y's, everything will have a full octet. So the formula is X2, Y3. Oh, okay. Yep. The reason why it's X and Y is not real elements. Otherwise, you could just Google it. Can you do an example of a fusion rate from test 3? Sure can. So let me go to test 3 of fusion. Test 3. So fusion. Okay. So let me clear this out. So fusion rate. So I have a sample of gas that has, and these are all variables. So I'm going to just make this up. So I have a sample of gas. So gas 1 has a molecular weight of, let's just say, 100 grams per mole. And it has an effusion rate, let's say, I don't know, 200 meters per second. The same amount, so same weight of a different gas, gas 2, which has a molecular weight of, let's say, 150 grams per mole. So I have two gases, gas 1 and gas 2. They weigh the same. They have the same amount. So, sorry, I'm sure I'm confusing you. I have the same amount of each gas, right? So I have the same number of molecules of each gas. And I want to know, based on gas 1, what is the effusion rate of gas 2? And so for this, I actually need to look up the equation, because this is one of the few equations that for some reason I can never memorize, which is why I usually give people equation sheets. But this is Graham's Law of Effusions. Now I know there's like a square root in there. There it is. So Graham's Law of Effusion rate says that the rate of gas A divided by the rate of gas B is equal to the square root of molecular weight of gas B divided by the molecular weight of gas A. So I'm just going to call gas 1 A, gas 2 B. It doesn't matter which one's A and B. All that matters is that you keep A and B together, or you keep the rate with the molecular weight. So the rate of gas A is 100. Or sorry, I'm looking at the wrong thing. The rate of gas A is 200. That's my effusion rate. Divided by the rate of B. I don't know. That's what I'm trying to figure out. It's equal to the square root of the molecular weight of B, 150, given here, divided by the molecular weight of A, 100. So let me pull up my calculator. So that equals the square root of 150 divided by 100. So 200 divided by rate B equals 1.22. And I'm going to continue this over here to give myself more room. So I'm going to multiply this variable rate B by each side of the equation. When I do that, I get 200 equals 1.22 multiplied by rate B, whatever this rate is. And I divide each side by 1.22 now. The rate of my second gas, therefore, based on this equation, is 163.9 meters per second. So that's how you do Graham's law of effusion with that equation. Can I go over formal charge of an atom from test 4? Sure. All right, so formal charge. The question was, I have HCS, that looks like this. And sulfur had 7. What is the formal charge of each 3 atoms? So let me erase some stuff. All right, so formal charge, the equation for formal charge is the number of valence electrons minus the number of lone pair electrons. So I'm going to call that LPE, lone pair electrons, plus the number of bonds. And you have to do this for each atom. So hydrogen has 1 valence electron. Remember, we get that from the periodic table and from what we talked about in test 3. So hydrogen has 1 valence electron minus the number of lone pair electrons. There are no dots around hydrogen, so it has 0 lone pair electrons plus 1 bond. So hydrogen is 1 minus 1. The formal charge of hydrogen is 0. Let's do carbon. Carbon has 4 valence electrons minus, well, it has 2 lone pair electrons, so that's 2, plus 1, 2, it has 2 bonds. So this is 4 minus 4 equals 0. Sulfur. Sulfur comes with 6 valence electrons minus 2, 4, 6. It has 6 valence electrons and 1 bond plus 1. So the formal charge of this sulfur is minus 1. So that's the answer, 0, 0, minus 1. Can you go over question 12 on test 4? Let me see what that is again. Question 4, question 12. Oh, okay. Let me share my screen once I get up like my version of the test then. So stop share and share this. All right, so the question is like ionization energies. How can we tell which element goes to which ionization energy? And remember with ionization energies that, well, first let's just say, what is an ionization energy? And it's the energy to remove an electron. And generally, the more electrons you try to pull off, the harder it is. So that's why we see energy go up every single time. However, valence electrons are relatively easy to remove. And core electrons are really hard to remove. So what this is saying, 1, 2, 3, 4. Well, that is not the correct answer. The correct answer is aluminum. So I will have to go and change that and change people's grade. I did not realize that was a typo. What this says is like, how many valence electrons are in this molecule? And it should be aluminum. I don't know well, what I was thinking when I selected silicon there. Because silicon has 1, 2, 3 valence electrons. So you remove one electron, that's IE1, second electron, that's IE2, third electron, that's IE3. Then when you try to remove the fourth electron, you have a big change. So I will make sure everybody's grade is changed for test 4. So you might see your grade go up, or you might see your grade go down, because I have to change that. So be aware of that. All right. Can I do questions 5, 6 on test 3? Maybe. While I look for that, can you, whoops. While I look for that, can you tell me what questions 5 and 6 were for you? Because everybody has a different order of questions. Oh, I just saw you. Okay. So test 3. Categories. Balloon inflated, asking how much work is done. Okay. Let me take a look at that. All right. So let me pop back up my my board. All right. So the question is, let me clear all this nonsense. I have a balloon. And this balloon is inflated from 0.109 liters to 0.633 liters. And the pressure outside the balloon is 8.25 atmospheres. And the question is, how much work was done? All right, and the conversion factor we need for this is 101.3 joules equals 1 liter atmosphere. And the equation is to calculate work when you are like changing volume against an external pressure is equal to negative what is the pressure that you're pushing against multiplied by the change in volume, which is delta V. Remember when we see delta, that's final minus initial. So the atmosphere is negative 8.25. So that's our pressure multiplied by our final volume is 0.633 minus our initial volume of 0.109. And these are both units of liters. So calculate that. Whoops. I can get out Excel. So the work that is done by that balloon is 4.323 liter atmospheres, negative. Now I just need to convert that to joules. 1 liter atmosphere is 101.3 joules. So the amount of work done is negative 438 joules. So that's how you calculate work when you're changing volume against the pressure. And the other question was, When you have two different metals, what's the mass of the metal? Yeah. All right. So the other question. I have two metals. I'm going to draw them as two different blocks. I have metal B and I have metal A. And they're in contact with each other. Metal A weighs 31.91 grams. Has a heat capacity of 2.92 joules per gram centigrade. And the initial temperature is 82.43. And metal B has a heat capacity of 0.542 joules per gram centigrade. Temperature initial is 56.62. And the final temperature for these two metals is 61.46. All right, so the concept that we have to understand for this problem is that when two metals are in contact, they're exchanging heat. So the heat lost by one metal is equal to the heat absorbed by another metal. So the heat of metal A is equal to the negative heat of metal B. So that's saying like these two are exchanging heat. One is gaining heat, one's losing heat, but it's the same numerical value. It's just that the one's gaining, one's losing, so that's why we have the negative sign. It doesn't matter which side the negative sign's on. And to calculate heat is mass times heat capacity times the change in temperature, MC delta T. So let's start figuring this out. So Q of mass A, which is the mass of metal A. So that should be metal A. I said mass A, but it's the mass of metal A. So Q for A is equal to 31.91 times the heat capacity, which is 2.92, times delta T, which is final minus initial. So 61.46 minus 82.43. That is equal to negative heat of B. Heat of B is the mass of B. Well, we don't know that. That's what we're trying to figure out. Times the heat capacity of B, 0.542, times the change in temperature. The final temperature was 61.46 minus the initial temperature, 56.62. So solve for M. And so let me get my calculator up, aka Excel. So this is equal to 31.91 times 2.92 times 61.46 minus 82.43. So the left side of the equation is negative 1953. And this is equal to negative, let's do the right side of the equation, 0.542 times 61.46 minus 56.62. The right side of the equation then is negative 2.62 mass of B. That's what that M is. Divide each side by negative 2.62. The mass of metal B for these weird variables is 745 grams. Test 3, can you go over, there's a mixture of Ne and At gas. Sure, let me pull that up. Argon gas, okay. Oh, okay. So let me share this. So there's a mixture of neon and argon gas. Neon has a pressure of something atmosphere. So let's just put 2 atmospheres. The total pressure of the mixture is B atmospheres. Let's put 3 atmospheres. What's the partial pressure of argon? All right, so we have a container that has 2 gases, neon and argon. I know that neon has a pressure of 2. I know in total, these have a pressure of 3. So what's the pressure of argon? It's the total minus neon, right? So in this case, it would be 3 minus 2. My pressure of argon is 1. So with partial pressures, remember that gases, their pressures are completely additive. So if you have 2 separate gases, and you know the pressure of the separate gases, if you add them together, the pressure is just going to be those pressures added together. And this goes back to the ideal gas law. The ideal gas law says that gas particles don't interact with each other. They basically ignore each other. They act independently of each other. Therefore, pressures are additive. Yeah, I mean, it's hard to think straight when you're doing a test. Not all chemistry has to be hard. What else? And while you're thinking, that does remind me of something. Let me go to course content. Did I put it up yet? All right, so I didn't put it up yet, but I made it. I'll put up an Excel spreadsheet that will walk you through how to calculate what you need to get on the final exam to get a certain grade in the class. So I always get those emails, and it'll be a lot easier if I just give you the tool that I use to say, like, if I want to get a B in the class, what do I need to get on the final exam based on my current grade? So I'll make that available under course content here today, because I haven't made, but I guess I just didn't put it up yet. Any other questions? So on test 1, what is the name of this compound? Iron something chloride. Sure. So what is the name? What is the name of FeCl2? So for naming, first off, you have to notice that this is an ionic compound. So this is a metal, this is a non-metal. And for ionic compounds, there are different naming schemes we use to name the compound. If it's a transition metal, and a transition metal is not column 1 or 2, or Al, zinc, or silver. If the metal you're looking at an ionic compound is not in column 1, is not in column 2, is not aluminum, zinc, or silver, you have to use Roman numerals to name it. And the Roman numerals tell you the charge of the metal. All right, so now that we're at this part of chemistry, there are a lot of different ways that I've actually taught you to know what the charge of chlorine is. The easiest way is just to remember that all halogens, so fluorine, chlorine, bromine, iodine, halogens always have a -1 charge. That's what they do in reactions. So if I have 2 chlorines for every 1 iron, then the iron must be +2, right? Because if we do like a Lewis structure diagram of this, chlorine always comes with 7 valence electrons. That's supposed to say chlorine, by the way. We don't know how much iron comes with because iron is transition metal. But if I had 2 chlorines for 1 iron, that means iron must have had 2 valence electrons. So it was +2. And so we say this is iron 2 chloride. So you name the metal plus the charge of the metal, and then the non-metal, and you just add "ide" to it. Remember, we only do the Roman numerals if it's not column 1, 2, aluminum, zinc, or silver. If it is one of these, then we do not use the Roman numerals. For example, MgCl2, magnesium's column 2. So we just call this magnesium chloride. And the reason behind that is that we know the charge of these metals. These metals in chemistry always have the same charge in reactions. Column 1s are +1s. Column 2 is +2. Aluminum is 3. Zinc is 2. Silver is 1. But something like iron has a lot of different charges it can take in chemistry. So we have to tell the reader, what form of iron we're using. Non-metals never get Roman numerals. No, the only thing that would ever get a Roman numeral is a metal that's a transition metal. Anyone else have any questions? I can probably do maybe 1 to 2 more before I have to go eat before my next meeting. But I will say, if you're going over the testing, you do have questions, don't hesitate to email me or set up a meeting with me if you want to have some back and forth. That's what I'm here for. You have access to somebody who's been in college, since 2005 now, in some form or another. So feel free to pick my brain on this stuff. No problem. If I wasn't doing this review, I would I'd be eating lunch right now, but otherwise I would just be making your final exam. So. Last call for questions. Anyone have something off the top of their head that they want me to go over? Oh, and that reminded me for some reason. I had to put one more thing in for your grades. Pearson was down over the weekend, so you might have noticed that the homework grades aren't up to date. But at this point in the semester, don't expect the homework, like 100% on your last homework assignment, to change your grade like at all. This deep in, like each homework assignment counts for very little against, everything that's already been graded. So if you did do like your homework and it's all complete, you might see like a little tick up on your overall grade, but not too much. All right. Well, since I'm not seeing any other questions come up, yeah, don't hesitate to message me. You have until Friday at midnight. The only thing I ask two things that the semester is winding up. One, please don't email me like at Friday at like 10 or 11 and say something just came up. I cannot take my final exam. Can you give me an extension? That's going to put me in a really tough spot because you have 48 hours to do this. So do not expect to take it at the last minute and then, oh no, my internet went out. Please don't put me in that situation where it's like you're forcing my hand. Two, this happens every semester. Please do not ask me to round up your grade. That's a decision made by me and me alone, if I want to do that. You asking me does not influence my thought on it positively. So keep in mind, I do think that stuff over. And if it's going to happen, it will be of my volition. So please don't beg me to do that again. That's just really awkward at the end of the semester to get those emails. Yeah, that's what I asked. Yeah, test 4 will also be updated here, where I have to change the answer key to make sure it's aluminum. I think I actually had aluminum. Then when I was going over the test, for some reason, I don't know. I must have read the number wrong. But yeah, that'll be changed. So your test 4s will either go up or go down based on that. But yeah, since there's nothing else coming in, study hard. Good luck. Don't stress out too much. If you feel yourself stressed out, find a dog or a cat to pet. Science has shown that actually calms people down. So do that. Take some time to rest. And yeah, maybe I'll see you in a class in the future. Otherwise, take care.